we're sort of interested in the general idea of construction, which isn't necessarily about blocks, but it's more about the ability to take pieces and put them together and create something new out of that. And that's something that we as humans seem to do a lot throughout our history.
Is the answer to does it do it this way or does it do it that way? Is the answer always yes to both?
Yes.
It always is, isn't it?
I think so. There's so much interesting stuff that people come at from very different perspectives. And even if that perspective is super, super different, that it can be a really valuable thing to go and read about that and then try to take those insights.
This is Brain Inspired.
Hey everyone, I'm Paul Middlebrooks. In 1961, Heinrich Ernst, under the advisorship of Claude Shannon, developed a robot of sorts called MH1, a computer-operated mechanical hand. This thing was a robot hand that had tactile sensors, not a vision system, but a tactile sensory system, and it could put blocks into boxes. So a human would put a block somewhere on a table and a box somewhere on the table, and MH1 would search for the block, pick it up, then search for the box and put the block in the box. That's just one early example, of course. Fast forward almost 60 years now, and getting robots to do things with blocks is still a hard problem, as you may recall when I spoke with Raya Hadsel during episode 45. Well, today, my guest is Jessica, or Jess, Hamrick. These days, Jess is a research scientist at, wait for it, DeepMind, like everyone else, it seems. And she has a background in computational cognitive science, among other things. On the episode today, we focus on two main topics. We talk about physical construction, that is, her work using graph neural networks with deep reinforcement learning to create agents that build structures in a simulated blocks and glue kind of world to solve some tasks that she and her colleagues created. This is the first time on the show, I believe, that we've talked about graph neural networks, which are not new, but as Jess and I talk about, are getting more popular in AI these days. And we go on to talk about her work in mental simulation and how model-based reinforcement learning is a promising way to model mental simulation. We talk about some of the proposed ways that humans mentally simulate or represent mental simulation, which is not settled yet. And we talk about how machines might go about doing it. In the show notes, I link to the papers that we talk about, which I recommend to learn more about both of these topics. Those are at braininspired.co/podcast/51. You can learn more about Jess, like her work on the Jupiter Project, and her open source advocacy by following her on Twitter. She is at jhamrick, or visiting her website, jesshamrick.com. Just a reminder, I made a page on the Brain Inspired website where you can enter your email if you'd like me to keep you posted about the little neuroscience AI course that I'm developing. Well, I say little, it's probably going to be big. You can do that at braininspired.co/course, where I've also added a brief and extremely rough video explaining a little bit more about the course. If you are a Patreon supporter, or if you become one, like the obvious geniuses Ingrid, Piet, and Hal did recently, thank you guys, then you'll have access to a lot of what I create anyway, as I will use you mercilessly as beta testers and guinea pigs. Okay, even though I couldn't convince her that cognitive science should not be its own separate field, I trust that you will enjoy learning from Jess Hamrick. Jess, thank you for joining me on the show here today.
Thank you, Paul. It's really great to be on the podcast. Thank you so much for inviting me.
So I'm noticing, and we're on Skype, I'm noticing you're not wearing a construction helmet right now. How do you decide when you're giving talks whether to wear the construction helmet? I suppose it probably has something to do with what you're speaking about.
Yeah, so I guess you're referring to the talk that I gave at ICML a couple months ago. where I was presenting on one of our recent projects where we've been looking at agents that can stack blocks. And so we sort of we're referring to that project internally as the construction project, because we want to have agents that can construct things. And so that sort of became a bit of a thing, that we were construction workers and working on this construction project. And so at some point, Pete, actually, who's one of the other, Peter Battaglia, one of the other people on the paper, decided to buy a bunch of construction hats. So we had them around the office, and I was like, I'm going to take this to ICML and wear it during my talk, because I thought it would be fun. So
how did that go? Okay, how do you muster the gall to do that? And I guess that's a relaxed setting, perhaps. And then, first, just how did you decide that that's what you're going to do? And how did it go over is my second question.
I guess it was just, it seemed like a natural thing to do, because we had the hats, and it was sort of this joke that we had. And it was pretty natural to try to do that, I guess. But it actually went over really well. I think the talk was probably a lot more memorable as a result of that. I had lots of people come up to me afterwards and be like, "Hey, you were the one wearing the hat," or "Where's your hat? Why aren't you wearing it now?"
Did you quiz them after? Hey, do you remember what I even talked about, or what?
No, I didn't. Maybe I should have.
Yeah, it's a good idea. But I think that sort of, just learning more about you, I think that it seems obvious that you're a really good teacher, and I think that's a really good mechanism, right, to help people learn, having that prop. So
yeah, I think having things that sort of catch people's attention and make them. I guess even if they didn't necessarily remember that much about the talk itself, I had a lot of people who came to the poster afterwards who came because they remembered the hat, or they saw us wearing the hat at the poster, and then were like, "Oh yeah, that talk was interesting. Let me go buy the poster and learn a little bit more." So I think it really engages people more, and it helps them remember a little bit further. Either this is something that is interesting, I want to follow up with it further, or catches their attention more at the time. So.
Yeah, that's great. The salesmanship actually works well with communicating effectively, I think. So, So that's a good way to do it. Well, we're going to talk about construction and your work in that realm here today, and we'll talk mental simulation. But before we dive into that, so you have a background in, kind of a broad array of things, but psychology and computer science and engineering. And of course, you're at DeepMind now, using all sorts of methods to answer AI questions. But when you consider your place in all this, where do you consider yourself sort of on the scale between artificial intelligence and brain and neuroscience and cognitive? I hate to throw cognitive science in there, because I don't really, I feel like cognitive science should be just lumped into AI. I know that it has origins dating back to wanting to. But I'm going to say, where do you fall in the spectrum between AI and neuroscience, just to make it simple?
I see myself as really being really quite right at the middle. So even my whole background, I started out studying computer science and with an emphasis on AI when I was an undergrad. And actually, the earliest research that I did was in a robotics lab. And so I've always sort of been interested in how can we build things that are intelligent? And then I got interested in the human mind and how people think. And I was like, oh, this seems like this would be a really good angle to understand artificial intelligence more. And so that's how I got into psychology, and why I went to grad school in psychology. And then so I sort of went off in that direction for a while. But towards the end, I came back again towards AI, and I started doing, some work with human robot collaboration. I did an internship at DeepMind, and then ended up back here full time. So really I guess my whole path has really been kind of wiggling back and forth between those two ends of things.
Yeah.
So sometimes doing more on the human mind side of things, and sometimes doing more on the artificial side of things, but really being interested in both all the time.
So you smack dab in the middle. It's great that you're on the show then. That's a perfect fit for the show. What do I have to include cognitive science as a separate thing, or can I lump it in with AI? Or should I lump it in with neuroscience? What do I do with cognitive science?
No, I think cognitive science is definitely a separate thing.
They're all separate. Yeah.
Yeah, it's an overlapping thing. I guess so. Well, the origins of cognitive science really have it being like the intersection between a whole bunch of different fields. So neuroscience, AI, philosophy, anthropology, so on and so forth. And so I think, nowadays, I think like if you go to the cognitive science conference, you'll still find a lot of those different areas there, that the emphasis is more on the psychology side of things.
Yeah.
So it's kind of like, I think it's sort of morphed into a little bit more of like, it's like cognitive psychology, but in particular with the emphasis on either like computational modeling or the idea that the mind can be studied using like computational ideas, like that it is a computational process itself, which distinguishes it from a lot of other psychology. But I would definitely say it's distinct from both neuroscience and AI in and of itself.
See, and I know this isn't fair, but I lump psychology into neuroscience because, you have to have some sort of buckets that you put these things in. And I'm just like, do I have to change the damn tagline of my podcast to include psychology and cognitive science? No, I'm just going to keep two buckets and lump everything into those. I'm trying to. Anyway, congratulations on your first last author paper.
Oh, thanks.
So this is a paper called Structured Agents for Physical Construction. How did that feel?
It felt really good. It was really exciting to kind of be like, like after grad school, working mostly like by myself on projects and with my advisor, obviously. And I had a few collaborations as well, but I feel like in grad school, I was often working a little bit like more on my own and driving things myself. And so having this paper was sort of more like I'm driving it, but more at the level of like, here's like the important questions we should ask. And then also still doing a lot of the hands-on work myself, but then really getting to collaborate on that with a bunch of other people. And that was really fun and really exciting. And it was really satisfying to see it come out. And yeah, I was really happy with how the project turned out.
Do you like that role of the driver versus I know you're still doing hands-on things, but you're sort of directing, I suppose, right? In that role. Do you prefer that role, or do you like the technician sort of role more?
I like both.
Yeah.
I'm never happy with doing just like one thing or filling just one role.
Oh, I know from your record. I know. Yeah.
Yeah. So I think, it's really satisfying to kind of think more at a high level of like, okay, like here's a problem that like, people haven't really focused on, and we should really try to like solve this problem, and like what would the solution to that look like, and like, trying to like gather suggestions and ideas from the people that you're collaborating with and like work them out into a particular direction to follow. But it's also really satisfying to actually be the one to go in and make that happen.
Yeah.
So I think I really like both.
Cool. Okay. Well, so we're going to talk about that work in just a little bit here. And, who knows what order we'll actually talk about these things. So, but I also want to ask, so every time I talk to someone, I have this sort of long list of these broad general questions, and I never can get to all of them because I'm always running out of time. So I want to just start with one that is always on my list that I haven't been able to ask. As I'm talking to people, I kind of like cross things out or push them down. And this one always gets pushed down. But I wonder if I can just ask it up front here. The question is, what is a unit of meaningful progress in AI and in neuroscience, and just to you personally? Because in the AI world, you're like trying to solve things, right? Accomplish the task or whatever. And that's kind of I won't feed you. I won't lead you in any directions. Does that question make sense? And do you have answers to it?
Well, I guess a follow-up question in response would be like, what is the time scale at which you're referring to when you talk about meaningful units? Because I think that the answer is really different if you're talking about like the time scale of a few years versus like 10 years or 20 years.
Well, I want to let you just answer it, but because the word meaningful, right, is also just up for grabs in what it really means. I mean, to be sort of pessimistic, in academia, a unit of meaningful progress is a paper or a grant published, and I don't know how meaningful that really is. And I know, in the AI world, especially at DeepMind, you guys publish all your stuff too. So, but I would say a more meaningful unit of progress would be like figuring out how this particular model instantiation solves the task relative to another task, or building a new type of model or something like that. So,
yeah. Well, I guess I see there as being, there's sort of like two types of progress, maybe. One is kind of more of like a task-focused progress, and one is more of a methods-focused progress.
Mm-hmm.
So I think like we can certainly make like very meaningful progress on the task dimension by just at least this is, I guess, more maybe on the AI side of things, but saying like, can we get an agent to do X? Like, can we get an agent to play StarCraft, or can we get an agent to play Go? Or,
not just play, but beat the world champions.
Yeah, for example. Yeah. And I think that those are very like meaningful units of progress, because you take a problem that people consider to be very challenging and you show it's possible to do this.
Yeah.
Now, like, you can like pick at the solution and say like, all right, well, is this really the way we want to do it? Like, what about the computational cost or like any of these other considerations? But at least you sort of establish we can do this. And I think that is a useful thing to be able to establish. But then I think on the method side, it's also super valuable if you can say, okay, here's an existing problem. We already know we can solve it, but here we're going to come up with a new way of solving it that like we hadn't considered before. And I mean, there's many ways you could potentially try to do that. I guess to make it meaningful as opposed to just like an incremental thing, it would have to be kind of like coming at it from a completely different angle. Or maybe like solving maybe if you came up with a method that could solve like a different subset of problems, as opposed to like, you have one method which can solve a particular class of problems, a different method which can solve another class of problems, and then come up with something new that sort of unifies those or whatever would be also a very nice, meaningful unit. I think that those are more, I guess, like short-term things. In the long-term, meaningful progress maybe has something to do a little bit more with like, what are the sorts of like general abilities that we would expect like AI agents to be exhibiting? So, I guess, we can kind of, I guess, say we have AI that can do pretty well in like closed simulated environments that are like fully observable and deterministic. That's like, that class of problems, like we can do pretty well on. And so if you could say have another class of problems, which is like equally broad, that we could be pretty confident, like we can solve, would be like another, I think, meaningful unit of progress.
Yeah.
So, okay, all of those answers were on the AI side of things.
Yeah, yeah. Well, that's why I'm kind of asking, is because it's a little fuzzier on the neuroscience. I think it's a little more definitive on the AI side. What these measures that you could say are progress, many of which you just named off. Yeah.
Yeah. So I think, one thing to me that I see as being progress on like the neuroscience and cognitive science side of things is being able to explain behavior at increasingly more complex, being able to explain increasingly more complex behavior. So one thing we really like to do in the behavioral sciences is have these like really nice, well-controlled experiments where you know exactly like everything that's going on. You can do exactly the manipulations you want to do.
Yeah.
And then we can usually explain behavior pretty well under those settings, but it means that we're also limited to very like limited types of behavior. And so I think being able to explain, or maybe explain is too strong a word, but like
I was about to say explanation is its own conundrum. Yeah.
If we can predict behavior that's like in much more complex and like ecologically valid settings. So say if you could predict like, the exact like motor movement someone's going to make in a particular setting, or if you could, predict like maybe how people will play, these more like, very like say open-ended video games or something like that. I think that sort of thing would be a meaningful unit of progress because, even though we might not necessarily have the explanation to go along with the behavior, we at least have like a starting point that we can then try to dissect and get at that.
Yeah.
But I think as long as we stay sort of focused on these very well-controlled things, we might get like little insights about, particular aspects of behavior, but we don't really know like how that gets instantiated in sort of these larger, more complex contexts. And particularly if we're interested in like the intersection of AI and neuroscience and cognitive science, I think, we want AI that's able to act also in these like scaled up ecologically valid settings. And so understanding how human behavior works in those settings is going to be a really important aspect to go along with that too.
Yeah. Yeah. When talking with a lot of people on the AI side of things, it's often about solving problems, right? So there's a problem, there's a finish line, and you solve the problem by, making the version that beats a chess player at chess, and things like that. And so that's a very measurable quantity. And it just struck me, I think just out of jealousy, coming from the neuroscience side of, just doing the daily work, like what's the goal here? The goal is to besides curing diseases, because that's very meaningful progress. But then it's to understand how the brain is doing the task, right? For instance, or just understanding what the task is, what's actually being done. And that's such a fuzzy, unsatisfying way to try to measure something. So coming from the neuroscience side, in my own head, if the goal is to understand intelligence, let's say, and we could unify the AI and academia, neuroscience, cognitive science world, that those are fuzzier goals. So that's why I'm curious what people have in mind, just as a unit of measure of meaningful progress. So, yeah. I appreciate everything that you said as well. So thanks.
Yeah. Well, yeah. I guess one thing to follow up on that is I think especially coming from the academic tradition in cognitive science that I did my PhD in, which is this idea of doing computational level modeling and rational analysis. The idea there is actually, in a way, is very similar to the approach that's taken in AI. It's in AI we say, okay, here's a problem, we want to get our agent to solve it. What sort of constraints, meaning the architecture or the reward function or whatever, do we need to apply here in order to get the agent to solve this problem?
Yeah.
And in cognitive science, or in this computational level modeling and rational analysis, it's kind of a very similar sort of thing. It's okay, here humans are doing some behavior in this context, and what are the sort of constraints that we think that they're optimizing for? And so the question is, in one case we're trying to infer what the constraints are that people are optimizing for. In the other case, we're trying to set the constraints just so we can get the behavior that's desired. But they're kind of very similar questions in a way.
Yeah.
And so I think there's some parallels there where if you can make progress on one, you can maybe make progress on the other too.
And you feel, just personally, like you're making progress, meaningful progress when you're, for instance, mental simulation and construction, these feel meaningful to you? And I'm not trying to bait you or anything.
I think so. Yeah. I mean, certainly my more recent work, I think, has more to say about AI than about neuroscience and psychology, though I think that there are interesting connections there that could be explored further.
Sure.
But I think on the AI side of things, with the work that I've been doing on construction, I guess the class of problems that people are focused on, they tend to be at least on the RL side of things, tends to be things like games or things like continuous control are kind of the two main pillars in RL, I guess, that you see a lot. And there's not a lot in RL that looks at tasks that are a little bit more things that kids might do, or simplified behaviors that humans might actually exhibit. I mean, so not to say that our block stacking agents are literally, they're not doing the same stuff that humans do, but it's more similar to maybe the types of things that you might do as a kid, because, kids love to stack blocks or whatever. So it has kind of a different flavor to it than I think a lot of the other types of RL tasks. And I mean, that's actually one of the things that we found, is that sort of the state of the art canonical RL agents don't actually work that well in these tasks because they have this different flavor to them.
Right. Okay. All right. Thank you for playing along. Okay. So Jess, as AI progresses, it seems to me that we're basically, digging deeper into the bag of intelligent behaviors and making machines that can do some version of those behaviors, like you were just describing. Things like image classification, you could describe that as a behavior too. Done. Machine learning, machine translation, done. But I've been reading about the early days of AI, when symbolic, good old fashioned AI, I'm making air quotes, was born.
Mm-hmm.
And it seems like the systems that they were making were inspired either by really scant knowledge of psychology, or their own sort of intuitions about how we think.
Yeah.
And so we've learned a lot since then, but there is still an infinity, essentially, to learn about how we think. So I've had people on the show that, they're using deep learning And they consider what they do more psychology, actually, because, they make these little tasks, right? And then they see if their deep learning nets and such can do the task. But anyway, they consider it more psychology than neuroscience that they're comparing these things to, because they're trying to teach machines to do tasks like humans do. And then they're looking at the representations in the artificial networks and seeing how they map onto what we know about brains and how the brain works. But these days, trying to keep up with just the rush of things coming at us, but it's like every day I hear someone talk about like some particular scenario, very specific scenario about cognition. Like, they'll say something like, remembering how to ride a bike, right? After 10 years, let's say 10 years elapse and we still know how to ride a bike because of procedural memory, or they'll say, well, humans can just be walking down the street and they were working on a problem they're trying to solve. And then boom, a dream that they had a month ago pops into their head and helps them solve the problem. And they say, well, humans can just do that, right? But machines can't do that yet. So we need to figure out how to do that in machines. So I'm kind of wondering, are we still playing the same game as in the early days, using these behaviors and maybe having ill-formed or incomplete, at least psychological notions about how these things actually work to build machines that do these things? So that was a really long-winded question, I suppose. But
yeah. So, well, I guess I think that there's two things. So I don't know if there's necessarily like anything wrong with like using our intuitions to guide scientific progress. Like, well,
that's what we do. We have to use intuitions. Yeah.
Everyone does that. All scientists do that. Not even, scientists that are working on AI, right?
Yeah.
So I don't necessarily think that there's a problem in and of itself to do that. I do sort of take issue with when people do that, but then they say, oh, we know this about humans, and therefore, like, that's why we're motivating this approach. I don't think you should motivate an approach in AI from human psychology unless like that's actually like a well-documented thing in human psychology. But yeah, I think that there's like, when that happens, I think it could be a bit of a problem actually, because then maybe people who don't know so much about psychology go and say like, oh, look, like lots of people are basing their, approaches in psychology, but these approaches are like too rigid or whatever. Like if you look back at like, good old fashioned AI, and then they have the wrong idea about like what can psychology provide for AI. But I think if you look at broadly at like the whole literature of like particular subfields in psychology, there are very important things that you can say about AI. So, I mean, and maybe these things are kind of obvious, but I think that they like bear repeating. Things like, that objects are an important like psychological construct that we like objects are so fundamental to cognition. And yet, like in most of our AI agents, we say, okay, well, we'll just hope that objects kind of like appear. Like in the representations, But from my point of view, I mean, if we know it's so important psychologically for humans, why not give agents the capacity to represent objects in some way? That doesn't mean you have to tell the agent exactly what an object is. You just want to give it some bias towards the idea that objects are a thing that they could use to reason about the world. Yeah. So I think that that's where like psychology and neuroscience can potentially really help to inform AI, is more in terms of saying like, here's this very important thing in psychology. There's like decades of literature on these ideas. It seems, given that there's so much research on this and it seems to be such an important part of cognition, that like that should be a thing in AI.
Build it in. Yeah.
Yeah. But it's not building in a specific thing. It's building in like a general
capacity.
Yeah. And I think that that's maybe what differentiates it from like approaches in good old fashioned AI, where people did actually say, oh, look, humans do this thing. Let's like build in this very specific behavior. And I don't think that that's necessarily the right thing to do.
I mean, it is interesting though, like even and we'll talk about the graph networks in a little bit. Even that, I'm reading it and I'm thinking that is almost like heuristics in some way, back when they built heuristics just to figure out what the best path through a search tree was, and think, the best way to approach a search tree and stuff. So, yeah. So, then I think, well, are we swinging back toward the symbolic AI? But I like the way that you phrase that it's not building the thing into it. It's building a capacity to allow things that we know that occur on psychological levels to happen more readily, essentially.
Yeah. I mean, I always think of it as just being kind of like there's a spectrum on like, how much inductive bias you have in your system. Good old fashioned AI was like, it was like all inductive bias.
100%.
Right?
Yeah.
It's like the system literally like it cannot like, there's no outside input that causes the system to really like act differently. It's all just like hard coded rules.
Yeah.
And like that's exactly specified by the programmer. And then sort of the like more like these big like end-to-end neural network architectures, they have maybe like less like hard-coded inductive bias in them. They still have inductive bias in them. They're not, I don't buy the whole like learning from scratch thing. Because I think they still do have inductive bias in terms of like the architecture that you choose and like what training data you give it and how long you train it for and which optimizer you use. All of these sorts of things are things that will influence the result. But they maybe have like, the inductive bias that they have is much more, I guess, like domain general in that it's not specific to a particular problem that you care about. But, and then you can have stuff that's sort of in the middle where you say, okay, things like a graph network, which basically makes the inherent assumption that the world is composed of entities and relationships between those entities. That's sort of like getting at this idea of like that, building the idea of an object into the system. It's not saying, here's how you perform on a particular task, but it's also making the assumption that there are these things that we care about and that, that maybe wouldn't work well if you try to like throw it at a problem where there aren't, discrete entities. Maybe everything really is like mushy, continuous, stuff. Then maybe you really don't want to use a graph network. But if you want agents that are able to act in the world that we live in, like this world does have a lot of structure and is very discrete in a lot of ways. And so it seems like it's useful to be able to identify like where along that continuum you care about drawing the line and then focus there.
Well, Jess, you've screwed up my structure. Speaking of structure of the show here, you got me all turned around, but that all backwards. But that's great. Let's put on our hard hats and talk about construction and graph networks, shall we?
Okay. Yeah.
So this is like your most recent work, and it's the last author paper that I alluded to, essentially. And you're basically teaching AI agents to build with blocks, essentially like kids do. I know that you backed off from, it's not really the way kids are doing it, of course. But basically, you made a set of building blocks tasks and tested a bunch of different types of models to see which one performed best. And you found that graph neural networks that use reinforcement learning a la model-based planning, which is like part of the mental simulation stuff that we'll talk about in a little bit, beat out the other approaches that you tested. So I'm not kidding when I say this. On my way into this little tiny studio that I'm recording in, I literally had to kind of climb over and step over the fort that my kids built in the living room and did not clean up yet, like their father told them to. So, yeah. So what is construction in this context here?
Well, so we're sort of interested in the general idea of construction, which isn't necessarily about blocks, but it's more about the ability to like take pieces and put them together and create something new out of that. And that's something that we as humans seem to do a lot throughout our history, right? Like we figure out like how to build like shelter from the elements. And now like in the last century or so, we've built even much more complex things like skyscrapers and like space stations. And like, we love to sort of like figure out new ways to innovate and construct things that allow us to do new things in the world that we couldn't do before. So that's kind of the idea behind construction. That's the grand view, at least, that we would like to aim towards. So what we did in this project was really just a very tiny baby step towards that, which is to say, okay, where does, like what sort of like more simple construction behaviors do we observe? Well, kids love to play with blocks. So let's do something with blocks. And it's actually something that, block towers are a domain that I've worked a lot with for a long time, basically since the beginning of my research career. One of my earliest research projects was also looking at towers of blocks, but in humans, and like looking to see how people make predictions about how those towers of blocks like fall over, like what directions they fall in. And so this is sort of like, the next iteration of that. But now instead of looking at humans, we're looking at AI. And instead of just making predictions about what's going to happen, we're looking at actually producing those construction behaviors and actually building the towers up. So the the goal in the tasks is there's like a few different objectives. They all involve like picking up blocks and putting them in the scene. There's some obstacles in the scene that you have to stack around. So you can't, if any of the blocks like touch an obstacle, then the game is over basically.
And you're equipped with a glue stick as well.
Yes. So you can choose to make blocks sticky, in which case you could, I actually think of it more as like you're dipping them in a pot of glue rather than.
Pardon me. Okay.
Yeah. Rather than a glue stick. Only just because, like, if anything sticks to it and any part of it, then
it's all sticky.
It's all sticky.
What about a glue stick that you have to cover the entire block with vigorously? How about that?
Yes, that's fine.
Okay,
yes.
Thank you.
So you can make some blocks sticky, and then they'll stick to everything, and so you can't like break those bonds. And then there's various tasks. So like one task, for example, is you see like the silhouette of a tower and you have to place the blocks into that silhouette to like sort of reconstruct the tower. And it's not just as simple as like placing blocks exactly where they need to go. You also need to decide like which blocks should I make sticky, because the tower might, not actually be physically stable without the sticky blocks.
And then in the task, there's a cost incurred to using the glue, right?
Yeah, so you can think of that as basically like, the glue is expensive or it's a limited resource or something along those lines, that you want to try to limit the amount of glue that you're using. It's also kind of was like an interesting parameter to tweak just from like the experimental design point of view, because if you allow glue to be, or sticky blocks to be free, then the easiest thing is just to make all the blocks sticky, because you don't have to reason about physics in that case.
Well, you didn't have to consider world economies to do this, though, did you?
No.
The supply of glue, supply and demand curves, yeah.
Yeah, luckily our glue is simulated, so it's it doesn't actually incur cost on the economics of glue. But so that's like one example. But then we have other tasks like stack the blocks to reach like a point in the sky, just while avoiding the obstacles. So that's it's almost actually more like a navigation task where you have to figure out where to place the blocks just to like weave in and out of the obstacles to get the stack to a particular point. And then we have another task, which is more of like building shelter. So you want to stack the blocks so that they cover the obstacles from above. So you can imagine like if it were to rain, then the obstacles would stay dry in the rain.
Okay.
And so these are like three different tasks that kind of have, they're different objectives, but they're all sort of in the same simulated environment. So it allowed us to explore sort of a range of behaviors. And then, so you could say, okay, how should we train an agent to do this? Well, like the typical response in deep reinforcement learning would be take an image of the scene and then give it to a CNN, and then have the CNN say a coordinate, for example, of where you should place one of the blocks into the scene.
Right.
So that's one option. You could say, oh, but like, Jess, you were just talking about how objects are important. So maybe, you should have an object-based representation. So then maybe the next like sort of standard answer would be, okay, well, you take an RNN and you allow it to process each of the objects in the scene one by one. And then you have it at the same as a CNN, you output like a coordinate of like where you want to place a block.
And these would kind of be the default ways to approach this, given our current, the standard library of deep learning tools, I suppose.
Exactly. Yeah. It's sort of like, the natural, like, here's your components, like, how would you assemble them to solve this problem? That's sort of like the natural answer. But it turns out, like, when we tried to implement those agents and train them on this task, they didn't actually do very well. The CNN actually worked okay. It actually depended on the task. Sometimes the CNN did a little bit better. Sometimes the RNN did a little bit better. But neither of them really did that well.
So someone said, screw it, let's go back to symbolic AI and use graph networks. Is that what happened?
Sort of.
No,
not exactly like that. But the motivation was kind of like the CNN doesn't really like directly parse objects. And the RNN has this problem where the order that you give the objects will have a big effect on that answer that it gives. So really what you want is something that can reason about all of the objects as discrete separate entities, but not where there's like this effect of like how the order in which you parse them. And so a graph network has these properties. So a graph network is a neural network that operates over graphs, where the graph is a collection of nodes and edges. So in the context of the construction tasks, maybe each object in the scene corresponds to a node in the graph. In our particular case, we chose just to put edges between all the nodes in the graph. And then they have each of those edges and nodes is associated with a vector or a tensor. So that might, in the input that might correspond to the object properties like position, size, type, these sorts of things. So then the graph network processes that graph and it gives you a new graph with the same structure, but like new activations on the edges and the nodes of the graph. And the way that it does that is by basically performing these pairwise computations between all the pairs of nodes that are connected. And so in this way, it doesn't matter the order that you give the nodes in because it does the same computations all over the graph, the same sort of local pairwise computations.
And like one time step essentially, or one, I guess that'd be one cycle, cycle of, what would you call it?
So we usually call them message passing steps.
Message passing steps, okay.
Yeah, so one message passing step is like one application of the graph network. It's called message passing because, there was an earlier paper called message passing neural networks that they basically it's a particular type of graph neural network that the nodes compute messages and then they pass those messages along the edges of the graph to the other nodes, and then you can pass additional messages.
Oh, I see.
Yeah.
So I know this is not symbolic AI, but I was literally just reading about semantic networks from like Marvin Minsky days in the 1960s, and when they were trying to figure out language, and like basically a semantic network, worked on. They had nodes where there were basically these symbolic structures at the nodes that had little properties, little lists of lists, right? Was like a symbolic structure. And then there are associative links between the nodes that you could perform analyses on. And it's just like, oh, that's a graph network. And I know that they don't map perfectly on, but it does kind of harken back to that same way of representing the data, which is just an interesting parallel to me.
Yeah, I think that there's a lot of like connections with like graph networks and things that were previously explored. I guess in the same way that, like deep learning is really just like the evolution of a lot of stuff that have previously been explored back in those days too. So,
shockingly, things build upon each other. Yes, yes. As we advance. But
yes.
These graph networks aren't new. I mean, they're new to me. And now there's a whole new suite of things I have to learn. Thanks a lot, Jess. But
apologies.
because they're kind of exploding right now, right?
Yeah. So graph networks have been around. So like some of the earliest work with like neural networks on graph happened in like the early mid 2000s, like 2005 or so. This is like work by Marco Gori and Scarcelli and others. And they were looking at neural networks that operate on graphs. The formalism was actually not too different than what it is today. They were motivated by, various like actual graph problems, like so either like graph theoretic problems or, questions about like networks. So like, doing things like predicting page rank or various graph problems. There was also some early stuff looked at problems in chemistry, molecular chemistry. So say if you have a molecule, you can represent the molecule as a graph, and then can you predict like properties of that molecule, and these sorts of problems. And then graph neural networks didn't really get like too much attention for a while, and then they started picking up a little bit more attention, and people got interested in things like there's like a variant of graph neural networks called graph convolutional networks, which is kind of like a generalization of regular convolutional networks, but on graphs. But you can kind of see them as all being like in the same family of things. So they sort of have been picking up steam, looking at these sort of like graph centered problems, but I think one of the reasons why we're very excited about them is because we see them as really applying well to the types of like psychological constructs that we think are important.
Right.
Again, like going back to the question of like, entities and relations, and that has all sorts of, connections in like things like reasoning about analogy. Like, one of the most famous like theories in analogical reasoning is the structure mapping theory, which says that, people have these graphs that represent a concept, and they have another graph which represents another concept, and then you find the connections between those graphs, and that is how you do analogical reasoning. And there's also older work or other work that looks at various psychological representations as being graph structured. So things like how we represent like taxonomic structure, or how we represent even like color, you can see as being like a chain, right? Of like each color. Like if you discretize it, then it's a chain.
No, it's a really natural way to. It actually feels good to think of things like in the graph way. Like it feels very natural. And
Yeah.
So in your blocks world, how do the entities map onto graphs in the construction of blocks world?
Right. So the nodes in the graph correspond to the objects in the scene.
Mm-hmm.
So an object then has properties like its position, its size, its type. If you were it doesn't really matter. Like depends on what particular
Could be
domain you're
density
in.
or something. Yeah.
Yeah. Like you could also do color, anything like this.
Yeah.
In our case, like color and density don't matter, but
right.
you could represent that. And then, so those are the nodes. And then the edges can represent the relationships between those things. So in our case, we're looking at, can the neural network kind of learn what are the important relationships? But you could, for example, say we're going to connect blocks that are in contact with each other to represent like the contact relation. Or you could say, actually a prior paper that we had before the main construction paper, which I presented at CogSci last summer, was looking at a related task called the gluing task, where you have a tower of blocks and you have to choose pairs of blocks to glue together. So it's kind of a different notion of sticky blocks than in the construction paper. But and in that case, there you can represent on the edges whether that edge has glue or not, like whether those pairs of blocks are glued together.
Yep.
So the edges are very flexible and sort of can represent any types of relations that you might care about.
But you hard code that in, right? I mean, you have to make a decision about what they're going to represent.
Yeah. So one of the sort of big questions that a lot of people are working on, and I think we're starting to see some progress in this area, is basically figuring out automatically what things, like what is the structure of the graph that you should care about, and like what things should go into the nodes and what things should go into the edges. Because ideally, you would start from like sensory perception. You start from an image or something and then say, okay, let me extract the graph structure from this and then do my processing on the graph structure. And then, I get the output at the end. In the construction of work, we were starting directly from the graph structure to begin with. But yeah, I think if you were to like hook it up to, like an unsupervised, like object segmentation sort of system, it would have basically the same sort of behavior. So that's the way that the scene is represented as a graph. And then when you do like computation with that graph, that you can basically choose then any sort of like function you want as a result of that. So you can have functions on the edges of the graph, you can have functions on the nodes of the graph, or like you could have a function as like a global property of the graph. So you could say like, let me predict like whether the whole tower of blocks is stable or unstable, right? That would be like a global prediction that you could make.
Right.
Or let me predict, like in the gluing task, let me predict like which edge should be glued so that the tower remains stable. Or in the construction task, we also were actually producing actions on the edges of the graph, which corresponded to relative actions of which block should I place on another block. So I think like this way of like specifying structured actions on the different things that might be in a graph is a really like powerful language for building agents that are more expressive than your typical RL agents. Because your typical RL agents are like, you can like, you either have like a small set of actions like move up, left, right, down, maybe, or maybe they're like, something very low level like motor controls or torques or whatever. Or maybe they're like, you're controlling a cursor so you can move the cursor around and like, point and click or whatever. But these are kind of all very like, they're useful action representations to start with because they are the actual like actions that you get to take on the world. But you can sort of decompose it a little bit in the same way you can decompose like there's like perception and then there's reasoning, and like obviously the two are, the interface between the two matters a lot, but you can kind of study each of them a little bit in isolation. And I think you can do the same thing with action representations too. So you have like the actual like true action that you take in the world, but then there's the way that and then there's maybe the way that you can structure the actions in a more like say relational way, and then translate that into the actual actions you take in the world. So in the case of the block stacking, just to make it more concrete, because that's a little bit like, it's a little bit high level, is if we're going to place a block, I wouldn't say, pick up this block and place it at like position like 3.2, 6.7, like 5.4. Like, what does that even mean? Like, no one knows, right? I would say I'm going to put this block on, like, I'm going to pick up the red block and I'm going to put it on top of the green block, right? And so that's a much more structured way of specifying the thing that I'm trying to accomplish. And even though like my motor system does have to translate that concept of like, red block on green block into like a specific coordinate to bring it to, that's delegated to a different part of cognition. And so I think it's interesting to explore like, okay, what are these more structured ways that we can think about performing actions onto the world? And so this was sort of one way of exploring that in that was basically the action representations that we had was pick up a block and put it on top of another block.
Since we're talking about the concrete examples of the blocks, then what did you find?
Yeah, so I mentioned earlier, we tried these other agents like the CNN and the RNN and stuff. They didn't work that well. But when you do both, so with the graph networks, there was sort of two choices that we had to make, and both of these were important. So the first choice was the actual like structure of the problem as a graph itself. So you can take in the input scene, structure it as a graph, run your graph network over that. But then you could just like predict a single like global action to take, which would be like put the block at this coordinate. So that's like, it's a structured representation, but an unstructured action. You can also choose to make the actions themselves structured. So you can then have the structured graph representation, which then supports structured actions like relative actions, like place a block on top of another block. And so we found that the graph structured representation was actually like less important than having the structured actions. Having the structured actions was really the important part. But even if you give like more like structured relative actions to these other agents like CNNs and RNNs, then that helps their performance too. But it's like really the combination of like the structured actions and the structured representations together in conjunction that gives you the ability to train agents that can do really well at this task. And so we saw that our agents were basically, on some of the tasks, they basically completely solved it. And other tasks, they're very close to ceiling performance, not quite, but almost. So like in the silhouette task, which is the one I mentioned, where you see the silhouette of the tower and you have to, fill it in with the blocks. That one, the agents are completely able to solve.
What do they have problems with? Is it the one where they cover the obstacles?
Yeah, that's the one that was the hardest task for them. So it's hard for a number of reasons. So one reason why it's hard is it's sparser reward. So you have to like place multiple blocks in order to actually cover it, and then you don't get any reward until you cover any of the obstacles. It's also very, you have to be very careful in where you place the objects, because if you collide with any of the obstacles, then the game is over. So, and you don't get to, retry. So, I think this would actually be a very hard task for humans to do too. If you didn't give them an undo button, I think people would be pretty bad at this. But it's also hard because, there's multiple obstacles you have to cover in order to cover all of them, you really have to like compose the blocks into like multiple structures. So, you can't just like, cover this one and then cover this one and then cover this one independently. You have to sort of cover them in a compositional way. And so we saw our agents come up with some pretty cool solutions. Like they decided to build these T or umbrella structures. So there were three sizes of blocks, like little square ones and then like two longer rectangular ones. So they would stack up the little square ones and then like place a long one at the top. And then they would like maybe do the same thing on the other side of the obstacle and then place another long one like right in the middle. So they build this like big arch all the way around it.
The glue is infinitely strong?
So in this task, actually, the glue was very, very expensive. And so the agents didn't really use it in this particular task.
Okay.
So this was all like their reasoning about the physics of this in order to keep it stable.
So they're building arches.
Yep, they're building arches.
Yeah, that's cool.
That was one of the things we really hoped to see when we started the project. We were like, can we get agents to build arches? And because that seems like, obviously these aren't real arches, It was a feat of human engineering to figure out how to, curve them and like place the keystone or whatever. But, we were like, okay, like a simple version of that still seems like it would be a nice like illustration of that the agent knows something about construction, as if it can build arches. And it can, so.
What's next? Flying buttresses?
Probably that's a bit far off, but
okay.
But I think, I would like to see the agents continuing to do, harder versions of these scenes. So in these tasks, like the largest scenes that we had like 40 to 50 objects in them. But I mean, humans like construct things with many more parts to them. And part of the reason we're able to do that is with, using things like abstractions, like we build this part and then we build this part and then we can compose those in like larger parts together. So I'd like to see agents being able to solve even larger and more difficult scenes. I think exploring like other types of physics would also be super interesting. So, here this is like really just like statically placed objects that can maybe fall over, but you could consider like other sorts of moving objects or like, even like maybe deformables or liquids or these sorts of things would be interesting to have agents that build in a way that also has to be aware of these other different types of dynamics.
Well, there's like so much more to talk about here. And there's a really nice, basically survey review that you're a co-author on with, is it Peter Battaglia?
Oh, yeah.
Yeah. All about the graph networks.
Yes.
So I'll link to that paper and, of course, the construction paper. So I kind of want to move on just in the interest of time. But do you think? First of all, are you all in on graph networks?
Yes.
And do you think when you're approaching a problem, do you think, how could I implement this in a graph network? Is that your first mode of approaching something?
Yeah. I mean, I don't think a graph network is always necessarily the right idea, but I treat it as like another tool that's in the toolbox. Just like, and one of the things that we tried to like argue for in the review paper was that in deep learning, we have these sort of standard, deep learning components like RNNs and CNNs and MLPs, and why not have graph network as another sort of standard tool in the toolbox? That some problems will just call for that, and that then you should use it in those cases. So I sort of consider it as like one of the many possibilities that I could use when approaching a problem.
But one of the advantages, if I remember correctly, if I'm reading it right, is that a graph network can kind of encompass all of the properties of each of those other types of networks, right? And handle the tasks that are you would traditionally use those networks for. A graph network can kind of handle all of them. Am I wrong?
Well, so in some sense, yes, but I think practically speaking, no. So, so I would say like MLPs are actually quite different from
multi-layer perceptron is what you mean by MLP.
Yes.
Yeah, that's
okay. And multi-layer perceptron is actually like a graph network usually uses multi-layer perceptrons inside of it. So, so I think, multi-layer perceptrons still like make a lot of sense if like your input data is like literally just a vector, has a fixed size, and you want a vector as output that's a fixed size, and that you don't know anything in particular about like the structure of that data. Mm-hmm. And that's basically like the assumption that we're making inside the graph networks themselves, is that for the nodes and the edges, like their attributes, we're not assuming any particular structure in those representations. And so we're going to process them with MLPs.
Yeah. Okay.
But then you can kind of see like RNNs as like maybe a particular type of graph network because it's a sequence. But the way that they've been developed, I think there's a lot of very different architectural choices or like smaller architectural choices that make these models actually like quite different from one another. So like even though it's sort of maybe at like a high level you might be able to use the same language to describe them, mm-hmm. I would sort of like treat them practically as different things.
Okay, so here's an unfair question. How do you map graph networks onto brains?
That is a bit of an unfair question because I didn't do my PhD in neuroscience, but
well, okay. Yeah. So a bit of the real question, I suppose, is is there? I mean, so deep learning networks. Everyone says that's how cortex works, which is going to be wrong. But so there is kind of this mapping onto like, well, okay, a deep network and the hierarchy in a deep network can map onto hierarchies in different brain regions as you process an image, for instance. Mm-hmm. Up to the image object recognition. So there's some at least similarity between the structure of like some types of hierarchical convolutional neural networks and brains. So I guess the question is, do you think at all in terms of, is this brain-like at all, or is this even, I guess, do you think more on the psychological level, and is this how the processing works at a psychological level, or do brains even come into the picture?
Yeah, I think more about it at the psychological level, like we know psychologically speaking, that people think relationally, and like we were talking about earlier, graphs play an important role. But yeah, just because my background is not really in neuroscience, I don't really
That doesn't mean you can't claim things about the brain. Everyone else does. Come on.
Well, I try to not claim too much about things that I don't know too much about. So I wouldn't want to make any strong claims about how graph networks might be instantiated neurally.
Yeah.
I mean, it wouldn't surprise me if perhaps you could find like relational structures in the brain too. And I mean, certainly like the brain you can represent it as a connected graph, at least loosely speaking.
Yes.
So perhaps there's something interesting there. But yeah, I don't want to speculate too much about that because I don't know so much about it.
Trying to get you. I was trying to trap you there. Okay.
Sorry.
Yeah. So just a transition here, and because I really want to talk about this mental simulation review that you've written. So everything that we've been talking about with your work has been physical construction. But you mentioned something at the very beginning that or maybe I just inferred this from what you were saying, that it doesn't necessarily need to apply to physical construction, that it could apply to abstract concepts as well, and constructing new ideas from other abstract concepts.
Yeah.
So maybe this is a good time to talk about mental simulation then. And so you wrote a great little review of how mental simulation could be carried out in the deep learning regime. It's called Analogs of Mental Simulation in Deep Learning, in Current Opinion of Behavioral Sciences. I highly recommend it, and the figures are really well done. Like I said, it shows. I think that this really, your teaching ability really comes through in just how well the figures are put together and how well it's communicated. So,
thank you. I appreciate that.
Yeah, of course. Okay, so mental simulation you define as constructing. There's that word again. Mental models to imagine what will happen or what could be. And of course, we do a lot of mental simulation as humans. So what are some behaviors that do and don't require mental simulation?
Well, it's a bit of a thorny question to answer, just because if you know anything about the history of mental simulation in psychology, you'll know that it's fraught with debates about what exactly is mental simulation. So it sort of depends a little bit on who you ask. But yeah, I mean, my definition is basically the one that you just gave, which is that it's the ability to make predictions about either future states of the world or alternate states of the world. So like the way that the world could be. And there's an additional component to it, which I didn't get so much into the review article because of space constraints, but that there's a notion in which it can also is something that can be kind of applied iteratively. So mental simulation is like, you can imagine what would happen if I say, like throw this ball at a window, and then you could say, okay, well, I can imagine, maybe the window will break and whoever's house it is going to be upset with me. And then I could say, okay, what's going to happen after that? Well, maybe they'll try to get me to repair the window or pay for it or whatever. You can keep doing this. You can say, okay, what will happen after that? And after that.
So you run it again. Yeah. And eventually you have one where you become really good friends with the person's window, with the person you broke their window. Yeah.
Yeah, exactly. And that's sort of in contrast to, there's other types of thought, which are heuristic judgments might fall into this, though it doesn't necessarily have to use the word heuristic, just anything that may give you a prediction, but can't necessarily be like applied iteratively in this way. So, for example, in some of like the previous work that I mentioned earlier, where we were like looking at, how people make predictions of like where blocks will fall and stuff, like we found that if we ask them to make like a prediction very far in the future, like how far out are the blocks going to fall, as opposed to just saying, will the blocks fall or not? People didn't seem to be using mental simulation so much in those cases. They were using like just the heuristic of like, if the tower is taller, then the blocks will fall further. And that gives you a pretty good prediction, but it doesn't tell you anything else about it. If I just say, okay, it's tall, so the blocks are going to fall far, but then I can't say, okay, let me apply that again. It's like a no-op, right? It doesn't give you any additional information beyond that. Yeah. So that's kind of the distinction that I like to make.
Okay. So one challenge with mental simulation is that we don't even know how to represent it. We don't know how humans do it, really.
Yeah.
And like you're saying, there's this fraught, I guess, historical debate on how humans do it. So I don't know if we can, let's just start with natural human animal mental simulation. So the examples that you use in the paper are mental imagery, like rotating objects in your mind is kind of the classic one. You also talk about learning by thinking, which is an example of that would be simulating practicing the piano in your head, and then the next day you're actually better at the piano piece that you're simulating. So it improves your skills just by simulating it. And then the third example is the control of simulation, which you've done research on, and that is whether to even simulate or whether not to simulate, like the example that you're just describing. So I'd like to use one of these, to sort of tie into the work in AI. And is mental imagery the easiest, or do you want to talk about the meta control?
Well, I guess it sort of depends on like which aspect of AI you want to talk about. Because I see like the meta control is like very closely tied to the questions surrounding planning.
Right.
And things like mental imagery are more tied to like what are like the representations that we use to learn like forward models of the world.
Well, let me ask about, okay, so you talked about the different, sort of the debate on how these things are represented in our minds.
Mm-hmm.
Do you want to just talk about a few of the examples for in the case of mental imagery then?
Sure. So the classic like debates of mental imagery, sort of the work on mental imagery sort of started with like the rotating these like 3D objects, like the work of Shepard and Metzler from the 70s.
Tetris-like 3D objects.
Yeah, exactly. And sort of the conclusion from those experiments was the way, like, so the actual experiment there is like you see these two images of these like Tetris 3D like objects. You have to decide, is it like the same object in each image, or are they different objects? And they're either the same and that they differ by a rotation, or they're different in that like one is like a mirror image object of the other. And the conclusion from the experiments is that people like mentally imagine the objects rotating in order to compare them the same or not. And so this sort of kicked off this whole literature of work on mental imagery, of looking at like, like tell people to imagine that they're looking at a map and that they're looking at the house. So like you get people to memorize a map and you say like, okay, you're looking at the house. Now like imagine that you like, are looking at the lake, and you see like, the amount of time it takes people to say, okay, I'm now looking at the lake is different depending on how far away the lake is from the house.
Yeah.
Or like you can say, okay, imagine like that you're looking at this image, but it's like, it's really up close. And then you can say, okay, imagine that you like zoom away from that image. These are all sort of these like manipulations of these images that people have done experiments on. And a lot of this is the work of like Stephen Kosslyn and others. So Kosslyn's, take on the results of these experiments was that people are doing mental simulation actually on something that is image-like. So it might not necessarily be exactly an image, but it's like a 2D spatial array. It has image-like properties. It's spatial. But then there's sort of like another view of these phenomena, which is that, so this is like primarily the view posited by Polishin, saying that actually the computations that people are performing are symbolic in nature, and this like sense of the mental imagery that we have is just epiphenomenal. It's just sort of like, it's a side effect of the actual thing that's happening, but it doesn't actually have any causal influence on it.
Interesting.
And so those are sort of the two main theories. And these debates, like they started in the 80s, and I mean, I don't think they've actually technically been resolved.
Right. They just probably moved on. Yeah.
Yeah. I think most people in the literature tend to accept Kosslyn's view of things, but there's not ever been any official resolution to the debate.
The 2D map, essentially.
The 2D spatial, yeah. And that's because I think Kosslyn did a lot of also like, so the earlier stuff was all behavioral experiments, and then he went on to do a lot of like neuroscience experiments with fMRI too, showing like that there's a lot of like shared activation with actual perception and visual imagery. And so I think that convinced a lot of people.
Beyond the thought experiments, I suppose.
Yeah. So my feeling on these whole debates are that they're, I think that there's some like, okay, so let me talk a little bit about the review article now, because I think if you come at these sorts of questions, so you sort of take this whole debate and put it aside for a moment, and you say like, okay, let's think about like what is just like mental imagery in general. So if we say, mental simulation is this idea that of making like predictions about like future states or alternate states. And then you say, okay, what is that? Like, what does that look like in the context of AI? Then you end up in the realm of like model-based RL, basically.
So this is like the bulk of what the paper is about is how you map these mental simulation within the reinforcement learning world.
Yeah. So I'll say, I think that by looking at how AI views this, it tells us something maybe about the debates that people have been having in mental imagery. So we'll come back to that in just a moment after I describe like what it is in AI.
Great.
Okay, so model-based RL, the idea is, or planning. I mean, they're
same thing.
Technically, Well, they're technically separate, but they're similar.
Okay.
So we can treat them as the same for now.
Same thing for this show. Same thing. Yeah.
Yeah. So model-based RL is the idea that you have a model of the world, and that's a function that it takes in a state of the world, and it gives you, and maybe it also takes an action that you might apply to the world, and it gives you another state of the world. Mm-hmm. So, that might be if I have a block, and so, the state of the world is like the block is, on the table, it's at a particular location on the table, and then the action is like lift, then the resulting state of the world would be now like the block is in my hand and it's above the table or something.
Right.
So that model of the world just gives you the predictions of what's going to happen next. And then you can use those models in the context of actual like decision making and acting by using them inside a planning loop. So you can say, okay, like let me use my model of the world to predict what would happen if I take different actions, and I can pick the best action as a result of that.
So you run the simulation.
Exactly. You imagine. But then, like, if you actually look at the whole literature, there's lots of different choices that people make for how to actually come up with these models of the world. So, for example, one approach that some people have taken is to say, okay, you get your images, like, from your robot camera, and you just, like, learn to predict the next image. And so you don't worry about anything, about, like, sort of the underlying representation. You're just trying to predict the pixels of what's going to happen next.
Yeah.
But then there's other approaches that say, no, like, we want to actually, like, have a more, like, structured latent representation. And so they say, like, okay, we're going to first, like, encode the image as some, like, high dimensional hidden vector. And then we'll make predictions on that vector rather than on the image directly. So that's still, like, kind of more of, like, an unstructured way of predicting the future, but it's more structured in that you're at least assuming there's some, like, lower dimensional latent representation than the image itself. Mm-hmm. It's still high dimensional, but lower dimensional than the image, I guess.
Like predicting the hidden state, sort of.
Predicting the hidden state, exactly. But then you could also then say, like, okay, let's assume more forms of structure on that hidden state than just like a tensor, right? So you could say, okay, well, what if that hidden state is a graph? And then you could maybe, like, learn the forward model using a graph network. Or maybe if you know something about, like, what is the process that you're trying to model, like if you know its physical dynamics, maybe you say, okay, I'm going to assume, like, my latent state is, like, so if you know, for example, that you're trying to predict the motion of one object, but you don't know things like, its mass or whatever, then you could say my latent, state is the position and the velocity and the mass, and I have to, make predictions about how that changes over time. So you can sort of, like, again, like, go on the spectrum of more to less structured on the internal state of the hidden state in ways that either look more symbolic or more kind of like, more kind of like distributed representations. And then if you don't have the hidden state at all, you're at something which feels much more like spatial. And so now if you take this back to, like, the mental imagery debates, it kind of seems almost like, maybe when people argue for having, like, a spatial representation of mental imagery, what they're talking about is, actually making predictions at this image level. Mm-hmm. And when you're talking about having mental simulation be about, like, propositional representations, you're actually making predictions in a latent space, which is more symbolically structured. Yeah. But it also, like, it reveals something else, which is that you don't necessarily have to have one or the other, right? You could say, like, you can make predictions in the hidden state using, like, symbolic representations, but then convert them back to images and then use that as a way of gauging, like, are my predictions good or not? Because you can say it does look like, the thing that should be happening, or it doesn't look like the thing should be happening. So it's kind of like, it provides a very interesting perspective onto that whole debate, I think, by sort of grounding it in, like, what are the actual computations that are happening.
Well, is the answer to, does it do it this way or does it do it that way? Is the answer always yes to both?
Yes.
It always is, isn't it?
I think so. Yeah. I mean, I think a lot of times, like, with these debates, people care about different aspects to the question. Yeah. And so it's usually people are not asking about, like, this specific thing, is it X or Y? They're asking, you have this, like, larger question, and, like, here's one aspect of it on one side and another aspect of it on the other side, and, like, someone's talking about how one part of it works and the other person's talking about how the other part of it works. And so they might both be right because they're both different aspects of the same problem. But this is one of the reasons why I really like computational modeling in general, just because I feel like it forces you to really make concrete what is the thing that you're talking about. So if you say, like, the computations that are happening are image-based, then you have to actually like write down the computations that are image-based and show how that gives you the result that you care about. And actually, to be fair, Koslin did do this. He has like I think like the early 90s has like a computational model, which looks actually quite a lot like, transformations that you might apply directly to an image. So,
I mean, you've been talking about it in terms of these two different debated theories about how we represent mental imagery. But then there's a third also it's called the enactive, that has to do with coupling the imagery to actions strongly, essentially. So,
yeah. So this was actually like, it was a while before I discovered the enactive theory of mental simulation. Like I went and read all these debates, and during the whole thing, I was like, what about like the actions that people take? Like, doesn't that matter? And then I finally eventually stumbled upon the enactive theory, and I was like, oh yeah, this is like, here's people talking about this. Because it's not just about the fact, mental simulation isn't just like making predictions about the world. Like the reason why we make predictions is so we can act better.
Yeah.
Like that's the point of it. And so
if you're not
if you're not talking about that, then, you're missing like the reason why you're missing something important about like a reason why we might have particular types of representations, or the reason why we might have different structures in our computations might be because of like the actions that we're trying to produce. And so, the enactive theory actually looks, I think, a lot more like model-based RL. It uses more like the computational versions of like enactive theories tend to use older sorts of techniques like Kalman filters and stuff to explain the way that actions are produced. And so they apply a little bit more to like, I guess, like low-level motor control types of things. But I think, using sort of like the general framework of like ideas in model-based RL, either ranging from the low-level motor control side to like higher-level theories of cognition, I think is like a really promising way to sort of unify all of these different competing views.
So we're running out of time here, so I have to move on. So one of the things that we didn't talk about in this article is, you talk about the partially observed Markov decision process as the basis for all these things and how it ties it in. And so I recommend this article that you wrote, even just as a really overview of reinforcement learning based methods, because it's so clearly explained. So again, thanks for writing it. And it's exciting thinking about the possibilities, and it makes a lot of sense to use these methods for mental simulation. So carry on the good work.
Thanks.
So are you doing Jupyter work these days? You've done a lot of work in the realm of Jupyter notebooks.
Yes, I am still doing that.
You are? Okay.
Yes. So when I was in grad school, I started this one project that's part of the Jupyter ecosystem called NVGrader, which is it's a tool for creating assignments in Jupyter notebooks and then like doing the grading, and also like cool. It's since morphed into something that also handles all like the file distribution and all of these things that surround like having graded assignments in the notebook. And so I still continue to maintain that project. We actually I just made a release of the next release of that NVGrader version 0.6 this weekend.
This is essentially volunteer work, right?
Yes. Yeah.
That's so great. Yeah.
I really enjoy doing it. It's nice to, I feel like, contribute to open source projects, like, and have something that can then be used by everyone and shared by everyone. So it's really satisfying to me to work on these sorts of things.
Yeah. I mean, that's a passion of yours that we can't get too much into, but the open source, I know that you have a longstanding passion for that. You don't keep your blog up these days though, however.
No, there's too many things to do.
It's too many things to do. Yeah.
Yeah.
What's something that you wish you knew going into, let's say, undergrad or graduate school?
That's a good question. I think that one thing I wish I had known, and I keep having to remind myself of this, is that there's so much interesting stuff that people come at from like very different perspectives. And like, even if that perspective is like super, super different, that it can be like a really valuable thing to go and like read about that and then try to like take those insights. So I feel like with like graph networks is a little bit of an example of this. Like I wasn't really doing anything with like graph theory. These are like methods that like sort of come out of like people who are working more on like graph theory types of things. But it turns out to be something that's very general purpose and like very useful for like the types of problems that I care about. And so I think the same thing with like RL. I wish I had started like working on RL much earlier in grad school. But I was kind of like, oh, it's like this AI thing. Like, I knew a little bit about it. I took a class in RL when I was in undergrad, but I somehow I guess, just didn't really kind of come to appreciate that it was useful. And so I think I wish I had known to like just revisit concepts that might seem not that relevant.
I'm coming to terms with the fact that I think that you never appreciate anything first pass, second pass, third pass. You have to actually almost be an expert in something before you appreciate it. And so it's like you have to revisit these concepts over and over and over to then realize, oh, this is important for this various other reason. I don't know if I'm just a really slow learner or if that's just a universal rule.
I think it might be a bit of a universal rule, but I think one thing that can help, I think, is to talk to people who are experts and like really passionate in those areas. Because if like you go and you read, I don't know, at least for me, if I go and I read like a textbook or a paper or even like a blog post on something that I'm not really that familiar with, and that doesn't seem that immediately relevant, I'm like, okay, that seems interesting, I guess, but like it's not, really that relevant to me. But then if I go talk to a person who's like an expert in that and they're like really excited about what they're working on, and then, we talk, and then the connections sort of start to come out from that, I think. And that can be really motivating and a good way to do it, even if like you don't really know that much about that area.
Yeah, I guess one way to think of it is that when you become more of an expert in a given area, then all of a sudden things in other areas look different and you can use them in different ways. You realize how would you, this is not an easy question, but how would you advise someone in undergraduate that's interested in the interface of AI and, let's say, we'll just call it natural intelligence? How would you advise them to proceed? Like what should they do with their formal education versus like their self-education, for example?
Yeah, I think the answer now might look a little bit different from when I was an undergrad, which makes it harder to answer.
Yes, it's hard. Yeah.
Yeah. I think it's very important to like stay abreast of both fields, but also I think I would caution not to try to like be too in the middle. So, if at the very beginning of this, we were talking about how like I'm kind of right in the middle of both fields, but really
don't do what I did. Yeah.
Well, no, but it's more of like an average. I would say on average, you should be in the middle, but like spend some time like being an expert in, something in neuroscience or cognitive science and like know that area really well. And then go and spend some time like learning about something on the AI side and know that really well. And like that will give you like expertise in both areas. And, like people then can like respect the work that you're doing in both areas and you'll see like the connections between them. But I think trying to do something like squarely always at the middle is probably really hard because you don't get like the full expertise in either area. And I think also then it's just like a bit distracting because there's like so much stuff to like know about on either side. It's better if you can just say, I'm going to ignore everything on the AI side for now and just focus on like the problems that are relevant to human cognition. Or I'm going to ignore everything on the, the human cognition side and just care about the problems that are relevant to AI. I think that's a bit easier to become an expertise in or gather expertise in both areas that way.
Oh, I really like that. Do you think you should do them in serial or in parallel? I guess you have to do it serially, sort of.
Yeah, I probably serially, or at least like if you do it, it's definitely possible to have more than one project going on at a time, but I would say probably the majority of your time should be spent on one side versus the other, with maybe a little bit on the other side.
I like that. And then you average out right in the middle, just like you. Yeah,
exactly.
What's one trait of our intelligence or cognition that you think will be really hard to build into AI, general AI or AI?
Oh, I could spend a long time talking about that one actually, but I think succinctly is to say like strong generalization outside the training set. I think like there's something very unique about human cognition where we can think of ideas that are just like so like far-fetched and like far removed from like anything that we have actually experienced. We can say like, oh, what would it be like if we went to the moon? Like, how is it that we came up with that sort of idea? Like, that's not something like an AI can come up with because it's
yet.
I mean, hopefully, eventually, it could come up with those sorts of ideas, but we just are able to sort of like, transport ourselves mentally into these like, completely different worlds than the ones that we actually inhabit, and that seems to be a really like powerful part of cognition that AI really struggles with at the moment, and I think it will take us a long time until we get there.
How do you think we'll view deep learning in the history of AI, let's say 30 years from now or something?
I hope that we will view it more favorably than like people tend to view, I guess, like good old-fashioned AI. Well,
Yeah.
let me rephrase that, because I actually have a pretty favorable view of good old-fashioned AI. I think it was actually an incredibly like useful like stepping stone to get to where we are now. And even today, a lot of like our fancy methods, like AlphaGo, for example, use methods from like good old-fashioned AI, right? And so I hope in 30 years it'll be kind of something similar where we'll have a new class of methods that we're using, but we wouldn't have been able to get there without all of the innovations that we're making right now in deep learning.
But so the most, maybe 5 years ago, everyone's like, oh, deep learning, it's the thing. But now people are like, oh, whoa, deep learning is not going to get us there. And we need extra stuff to, compositionality and causality and things like this that deep learning won't get us to. So that's kind of why I'm, wondering if how important of a stepping stone we're going to imagine it was. So,
well, I think having the ability to learn, basically, I see deep learning as being like a method for acquiring a function approximator, and that's a very, very useful capacity just in general, right? Yeah. So I think we're still going to need to be able to have function approximators in the future. And so I assume we'll probably still be using something that looks a lot like deep learning. I don't know, maybe someone will like figure out how to do like, evolutionary algorithms for everything or something, and then it won't be quite deep learning anymore. But
they'll still the deep learning people will say, oh, it's just part of deep learning now. Everything's deep learning now because it's like a catch-all term.
Deep learning is like, I guess, like all of learning basically at the moment. It's like, yeah.
Moving the goalposts. Okay, finally, Jess, what do you think that AI will help us understand our subjective awareness?
Oh, that's I have no idea.
All right, we will end it there. Okay. I know you're really busy, so I really appreciate all the time. And keep up the great writing and keep up the great work. And so thanks, Jess.
All right, thank you very much for having me. This was really nice to talk to you and to be on the podcast.
Brain Inspired is a production of me and you. You can support the show through Patreon for a microscopic $2 or $4 per month. Go to braininspired.co and find the red Patreon button there. Your contribution will help sustain and improve the show and prohibit any annoying advertisements like you hear on other shows. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thanks for your support. See you next time.